so that should be up and running. So today, what we're going to talk about is multi-node communication and strategies, and how we can connect our applications together using Elixir, as well as the strategies that we can use once those nodes are connected to talk between them and to get our work done across the cluster. It is going to be a bit more of a tutorial style talk, so I'm going to kind of walk you through the code and walk you through some examples, as well as show the overall ideas. And we'll also show some of the patterns that I've used at Blitz to achieve this level of scale that we do, and show off some of the strategies that we use. So over the years, I've seen like a lot of Elixir usage, but not a lot of companies actually using multi-node environments. They either don't have a fully clustered setup, or they're just using a single node or maybe two pair for redundancy, but they're not actually connected. So I kind of want to show off what this looks like, because oftentimes we don't get that experience and we don't get to see what Elixir really has the power to do. All right, so first off, we're going to start off with just multi-node and how we can connect those nodes together, and then why we would want to do that in the first place. So in a lot of languages, being able to communicate cross-node is actually quite difficult. It's either done through some form of external API, or it's done through something like protobuf or GraphQL or REST. There's very rarely these tools within the language that allow us to just do this right out of the box. And so this is where Elixir is different and honestly amazing, because it has these tools right out of the box that help us to do these clustering and internode communication. On top of this, we have Phoenix, which is our major web framework, which is already set up for these multi-node environments as well. And so when you add new nodes together, provided that they're clustered, Phoenix will just get up and running with this automatically. If we're using sockets, it'll ensure that's all working. And so we can really, like, the tools that we're given in Elixir allow us to scale horizontally, which means like we can just add a new node at any time to achieve more scale. And we can do that out of the box with zero to minimal changes. And this is honestly so cool. I don't think I've come across any other language which is this easy to set up and scale horizontally across. So first, one of the things that we need to do when going multi-node is how do we connect node A to node B? And so this happens in a couple different ways. But one of the interesting things about Erlang is any form of communication between node A to node B will cause node B to actually connect to node A as well. And so there's a connection made when you do any form of communication between them. You form this bidirectional link between the two nodes. So there's a few different ways that we can like communicate between these nodes, but when I say any communication goes for connecting them, I really do mean like anything. So if you do something like a node.ping, which is not a connect call by any means, but that will still connect these two nodes together and form a cluster. That also means if you do something like a send, where you're sending a process message from another node, that will also cause a cluster to form. So it's important to know that like whenever you do this form of cross-node communication, you're going to get a form of cluster. So this is pretty awesome, and it's really nice to be able to form these clusters pretty quickly. And we can see an example is we can see these clusters being formed because we have this function to us called node.list. And so you can call this node module from anywhere in Elixir. It's one of the standard libraries that's implemented. And what this node.list does is it shows you all the nodes that we have in our cluster that are connected together. In this case, you actually don't see the node you're currently on, so you're only going to see all the other nodes. So in this case, we're doing this obviously on node B because we're only see node A. There is also a function called node, which is just part of the standard kernel. You can literally just type in node and call it, and it will return the current node. So you can add those two together to get a full list of your topology or your membership. So say, for example, we have another node, node C, that comes along, and we want to connect that into a cluster as well. To do this, we basically just need to do that any form of communication, and we know we're going to get a message back, and this will connect together. One of the other things that Elixir does is it actually enables us to build mesh networks. And so what this means is that once node C goes to node A and asks to be connected, or messages it and is connected into the cluster, node A is signaling back to node C all the extra nodes that are in the cluster, and that allows node C to connect to node B and set up a bidirectional connection to that, which means we get this sort of mesh network effect in Elixir where all of our nodes are connected to one another. And this just happens out of the box, so we don't have to do anything extra to set this up. As long as we can ping a node from one node, it'll set up these mesh network cluster situations for us automatically. So essentially, that's how we can connect nodes together. And so there are really good benefits to this because we can obviously send our messages across our cluster, but there's also some like downsides. So when you have big clusters, there's a lot of network traffic overhead that goes on. So when you have like a new node that joins in the network, then it has to update all those nodes because we're in a mesh as well. And so there does hit, like you do eventually start hitting limitations with clustering, but honestly, realistically, most people will never hit those. It usually happens at around like 60 to 70 nodes. So you can get to quite a high amount of nodes before you hit that. But that is just one thing to be aware of and keep in mind, is that there is a lot of traffic to maintain this mesh. So we've seen how now we've seen how to connect these nodes, and it's fairly simple. We can basically just use any form of communication, a ping, a send, and that one will connect our two nodes together. So there's really not much to do, right? So that's a really good way to, in basic, set up our nodes, but that doesn't have. There's a lot of like things that doesn't include, as well as there's no way to really do this initially on startup that we've set up with this so far. So with this, there's two modules that really help us to set up clusters when our nodes start, and that's going to be netadmin and libcluster. There are a few other noteworthy mentions here, like Peerage, but for the purpose of this video, I'm only going to demo these two because I found that in more than enough cases, these two are just fine to get by. In often cases, it's only libcluster, but we're going to show netadmin as well because it's actually one of the cooler modules. So netadmin is actually built right into Erlang by default. It's built into the box, which is awesome because it's basically one of those tools that we have that we just get with installing Erlang, and we can start using it right away. So there's two functions in netadmin that are really important to us, and that's going to be the world function as well as this host file function. The host file function is really interesting because what it does is it reads our host.erlang file, which is a file that is in our current working directory we can set up. And that file just looks basically like what we see here. We can just define our list of hosts in that file. In the case of localhost, that means that we're just in a dev environment. In prod, you might have something like your list of IPs. Or if you're in Amazon, you actually could even have like just the instance names itself. And that's really all that's inside of this host.erlang file. And so when you define those hosts, what happens is you can call this world function, and what will happen is each of the hosts in that file will be read, and then you'll connect to any Elixir nodes that are running on those hosts. So it's pretty cool because we're able to take this host file and just start listing out IPs or host names, whatever we want inside of that host file. And then we can use this built-in Erlang module, netadmin, and this single function world to read that host file and basically connect to all of those nodes. So, but how does that actually work? And so we can see an example of this by, again, just using, like, we can put localhost into a file. We can set up a node on localhost, or node 1 at localhost, and we can also then set up a second node with node 2 at localhost. One of the important things here is you'll see I'm using -s name as opposed to -name. And the reason that I'm using -s name is because when you use -name, you actually have to use a fully qualified host name, which by default will be your machine. Whereas if you use sname, you can actually specify that host name. So in this case, we can specify localhost as the ending instead of having to type a very long like host name of whatever my computer is. And so sname is kind of my preferred way to set this up, just because it's a lot easier to utilize when you're testing and running around. So once we've set up these two nodes, we can verify that they're not connected in any way whatsoever because we can call this node.list function, and we can see that there's nothing showing up. So there's no members, there's nothing in node.list. So what we can then do is we can then call this netadmin.world function, and because we had that host file set up, it actually goes and pings both of those nodes and sets up a connection between them. So immediately we've now had, like, we have this one function call that is able to go to all of our nodes, set up connections, and it's super simple, right? Like, it's basically pinging the nodes, and then we're getting back Pong, and we're connected. And there you go, we're meshed together. So really easy. We can confirm this, that like if you do a node.list now in the second node, even though it didn't do any work, it's also connected. So we can see that this cluster is set up properly. So it's really awesome. Like this netadmin module, I honestly think this is one of my favorite finds in Elixir, just because it's underlying Erlang library that already exists, but really helps us to set up these clusters and maintain this mesh network super quickly. So how this works, and we talked about the host file, is how this host file actually works is for each of the hosts in those host file, there's another function in the netadmin module called names. And what that does is it allows you to call it on a specific host, and it will go to each of those hosts and fetch a list of the names from this process called EPMD. So EPMD is a process that sits on each of our Elixir nodes, and this comes in when you install Elixir Erlang. EPMD is automatically set up on those nodes, and you can call it from the command line. EPMD essentially tracks each of the names that we use to start our Elixir nodes, and it'll also track the ports that those Elixir names are on. So one of the things that happens when you start an Elixir server is that a port is set up on a random TCP port somewhere on your computer. And so EPMD keeps track of these ports, and that is what's used for all Erlang traffic to communicate between them. So that's how we can communicate from one node to another, is it's using that TCP port in the background. So that is automatically tracked by EPMD, and we can see this directly by actually just calling EPMD with -names, and it will show us an example of all the nodes that are running on our system and what ports those are running at. So once we do that, we have our host file and it's being read, and it basically is automatically reading those EPMD names and going to and returning those so that they can be connected to. So let's take a look at an example here where we actually do this at startup in kind of a production system where we want to start up our nodes and make sure they're connected into the cluster immediately upon starting. So the first thing here is we have our task supervisor. The reason we have a task supervisor is because we want our task to be able to die and restart, and we don't want it to go too quickly. By default in Elixir, your tasks will only restart around 5 times before it actually just shuts down your system. So by having a task supervisor, we can actually customize the restart strategy and give it a few more opportunities to connect. Once we have our task supervisor set up, we can set up a restart transient for our task child and start a child of that task. What we can do, one of the weird things actually is that we are doing this within another task, and that's because we don't have the ability to set the restart on the task outside as easily as we do with the task supervisor. We actually just can't start the task on the task supervisor from this level. We would have to do it from another task, which is what we're doing here. So with the restart transient and the max restarts, this gives us around like 120 seconds to get connected. And if like that time is actually way too long for production, we would never want that. We probably want that lower, but for our cases here, this is fine. So once we have this task running and we know it's going to restart, we call this netadmin world module. And what this does is, and we've already seen what this does, so I'm not going to explain it again. But what it does here is if we only get one node, we basically kill the process. And so that way we know there's been nothing found. No nodes has found, so we're going to sleep for 1 second, and then we exit the process and kill it so that it restarts. Because the restart is transient, this will retry, and so yeah, that's where we get the 120 seconds of retryability. If we get more nodes, it will just hit OK, and so this will continue, and that way we know we're connected into the cluster, and so any new nodes joining into the cluster will also be set up in this way due to our mesh. So we can see this work, like this works pretty well. We can see an example here where, for example, we set this up, it wasn't able to connect, and then we set up a new node and it was able to connect to those two together. So within like 20 lines of code, we've managed to create a fully automatic cluster membership system just using the built-in tools available to us in Elixir and Erlang. Like how cool is that we could just do this out of the box with like just the tools we're given. However, like even though we can do this, there are some downsides and there are some inefficiencies to the process. And so that's why it's good to use a library to handle some of these edge cases for us. For example, we saw with the netadmin module, when we used it to connect to things with world, it pings every single node found in the host file, even if we're connected to those nodes already. So that's where something like a library can come along and make this easier for us. So we started talking about netadmin, and I also said we're going to talk about libcluster, and so we'll get into that file, into that library. And that library is essentially one that comes with a bunch of strategies. And these strategies are what are used to then determine how you're connecting to the nodes. So the three strategies I'll talk about today are Erlang host, EPMD, and DNS pull. Erlang, we're just going to go over a few of them quickly, and we'll dive into EPMD the most. But Erlang host is essentially the actual, it's literally just the netadmin module set up with a bit more efficiencies. So if you really like the idea of like a host Erlang file and using that netadmin module, just go ahead and use libcluster with Erlang host. It's going to be more efficient, and it's doing the exact same logic. It's just not calling the world function. Instead, it's calling the names function and then not pinging every single node, but just the nodes it needs to connect to. The second one we're going to talk about is EPMD. And so EPMD, we're going to dive into a lot more because it's probably the main strategy that I use in my daily Elixir use. But I thought DNS pull would be a worthwhile mention as well because it's quite common. I know fly.io uses it. And one of the most biggest utilities out of it is that it will just ping your DNS server. And anytime there's an IP address returned by it, it'll just attempt to connect to that. So with that in mind, let's go ahead and talk about EPMD a bit more and see an example of using that. So with libcluster, it's extremely easy to set up in our application. We essentially have to just add this supervisor here, cluster.supervisor, and this comes directly from libcluster. This is actually one of the weird parts that confuse me because most of the times when you import a library, the module is named after the library, but with libcluster, it actually isn't, and they just call it cluster.supervisor. So that I think that provides confusion to everyone, especially when using the docs. But as long as you're aware of the gotcha, it's totally fine. So once you have that, your parameters to the child are going to be the name, which you're going to have to define a name for the cluster supervisor, as well as the topologies. So the topologies are just defined up here in the top. And these are some of the most, this is really where the magic happens. So we have this ability to define a strategy, which we're just setting to EPMD. If we wanted to do the Erlang hosts, it would be there, or DNS pull, we could also set it here. And then each strategy takes a set of config. In this case, EPMD takes this hosts config. So we have like the list of nodes here, and these are the nodes that will be connected to from a libcluster standpoint. So we can see this working because if we start up a node, for example, here, we are just starting up a libcluster node, it's unable to connect to either node 2 or node 3, like we had it defined in our in the config here. So in the config, we have node 1, node 2, and node 3. And on our first node, because there's no other nodes to connect to, it just can't connect. When we start up the second node, it's able to connect to node 1, but not node 3. And node 3 is, of course, able to connect to all of them because they're already on live at this point. So there we have it. It's super simple. We're able to set up and connect to, connect to our nodes. We're able to use libcluster to connect them all together in a mesh, and that just happens automatically. So with even less code, like I think that was probably 10 lines of code for libcluster. So super easy to get set up. So this is really cool. But what is the actual point of doing this? Why would we need to connect the nodes together, and what purpose does this serve? And so this is a really good question because the biggest thing we need to ask ourselves when initially starting to cluster is, do we actually need to cluster at all? Do we have something in our servers that need to be connected together? For example, if we have a Phoenix app, do we use sockets? And I think that's honestly the biggest driver of Phoenix is if we use sockets or not. If we use sockets for Phoenix, in order to get messages from one node to another, say, for example, you have a user listening on one node, but a user on a completely another node is making the message to update the entire state, you need to be able to get those messages across your nodes. And so that's where clustering comes in handy. So you really want to know when you need clustering and how to do it. But if you don't need clustering, try and stay away from it because it does add overhead and complexity to your system. And if you don't have the value for it, don't use it. So at Blitz, we use clustering because one of the biggest reasons is we have a lot of networking or we have a lot of traffic that we need to process in the background. So we have for example, we have a message that comes in and it comes into Phoenix, and we basically do some logic to return data, and then we add that user or whatever information that's necessary to a queue. That queue is then processed by something like GenStage or Oban, and then or some form of Gen server, and then can be read from kind of outside of that web request and then on a completely different node. And so because it's happening on a completely different node, we know that our server, our web node, won't crash. And that is honestly one of the most important things when we're building large systems, is not crashing and letting all our users down. So at Blitz, we do still use this EPMD strategy, as I mentioned, and I'm going to show you guys our config because I think it's kind of cool to see. So it's really just a list of all these hosts together, and we're just adding them in. So each of these has a list of host names like 001, 2, or 3, and we're just aggregating all of these with some concatenations and just passing that to the host file. Super simple, right? Like very easy, and now we have a very big cluster that's all connected together. There's a few cases this doesn't work, and that's mostly in the case of auto-scaling. But for auto-scaling, you usually have some sort of other strategy, whether that's a DNS poll, or there's also strategies for specific providers, such as EC2, where you can basically ping different metrics from the EC2 nodes to connect them together. So now that we have these two nodes together, how do we actually communicate between them? And what are the patterns that we might want to use to do this? So there's three main ways that we can communicate with our nodes, and that's going to be process and kernel send, gen servers, calls and casts, and erpc. Process and kernel send are really the same thing underneath the hood. Both are just calling erlang.send. So I'm really going to try and be light on the explanation there because it's the easiest one, and I'll dive into the second two a bit more. So for process.send or kernel send, what you can do is really just send a message across a node. In this example, we're using IEX to register a process by name, register the IEX process by name, and then setting up a receive block. The receive block will just wait indefinitely until it receives a message from another process. And so that's what we're doing in the second node, where we send a message to that process that we've named IEX shell on node 1 with a message of hello. So we can see that we get back hello instantly. And if we look at node 1, we can see that we also hit the message and got triggered with I got a message hello. So this is pretty easy, and now that I've covered this, I'm going to move on to gen servers and erpc because I think those are much more fascinating, specifically erpc, but we also have to talk about gen servers as well. So with gen server, we can do similar things where we trigger a message to go from one process to another, and we can do that with the named servers or even PIDs that we get back from a gen server. I think gen servers are really cool in this aspect as well because these are all just like built-in tools to the Elixir ecosystem we have. So even if we don't use them on a daily basis, they're there ready for us to use. So in gen server situation, what our situation usually looks like is we have a process, say on node 1, that wants to call to processes on node 2. These could be worker processes where we either want to get some work done, or they could be some sort of process where there's state, where we want to fetch the state from that process. Most of the time it is some sort of worker. And so that process is essentially just going to need a way of directly communicating from node 1 to that worker process on node 2. So how do we get our message from that process on node 1 to node 2? And this is where it's actually pretty simple. So we're just going to set up an example gen server, and that way we can see how this works. This gen server is pretty simple. What it really does is it sends an interval every 30 seconds to refresh itself. It also seeds itself with the same function call, which is refresh. And so this handle info for refresh, which is called by the interval, it calls that refresh date function, which is also called by the seed. So it's essentially the same function call, just being refreshed every 30 seconds. And so that refresh date call could be doing something like an external call to an API or calling some sort of database node, whatever it needs to do to fetch and seed its state. It's an external process sitting somewhere on one node. So how do we now talk to this process that's on this one node? And we can do that by really looking at the name that it's giving. So the name that we assign our process is really important here, or else the PID that the process gets assigned is going to be really important. And similarly to when we do a handle, handle continue or handle cast, once we start up this process, we can simply use a call or a cast to actually address the process itself. In this case, what we can do is we can call it directly by the PID, but we also specify the node name. So you saw this is a very similar syntax to what we did with a process send and a kernel send, where we just pass in a tuple with the process name first and then the node name, and then we have the message after. So it's the exact same syntax, but it also works with gen server calls and casts so that we can do this internode communication. So this is really awesome. We're able to set up gen servers and have processes on other nodes that get called, but there are limitations to this. And one of the biggest limitations is the fact that we're on a single process. So in Elixir, one of our big limitations is that we're single process bound and we're limited to that single process. And so that means that we have to stay within that confines. So what we can do is use erpc instead, and erpc kind of saves our processing here. So with erpc, we're able to, instead of calling a server, we're able to execute remote code on a remote node. And this is much more scalable because a process is spawned on that node, and we're able to call it from, and we're able to basically execute that process remotely. And this can be spawned as many times as we want. We don't have that single process bottleneck. So this is something that we actually do at Blitz quite a bit. And let's just take a look at an example of this because it's quite simple. So one of the most common things for us at Blitz is to use data nodes to abstract away the layers of Postgres and to stop having to connect so many Postgres instances together. So instead of having like 60 nodes with over 1,000 connections to Postgres, we can have like a set of 5 nodes with 100 connections, and the rest of our Elixir app can reach to those. So in that, we have a data node with a context loaded onto it that's calling from ecto repos. In our resolvers, instead of calling this context directly, we use erpc to call the module on a random node. And so what this does is now it goes out to that node, fetches the data, and then returns it, and then goes into the resolver. So we've now unbound that single process limit, and we've been able to make this really quickly. Blitz has used this pattern really effectively to gain some really high levels of scale. We've used this to get nodes that are able to do over 3,000 RPS to adjust the database. And we've also used this to build analytics patterns where we basically take all of our traffic and analytics that come in and analyze it through data warehouses. And so to write to those data warehouses, we have to send all of our traffic to one node or to a set of nodes, which writes them to a file and then uploads those to S3. So we use erpc for all of this, and it is so scalable. It can handle 10 terabytes a day and over 3,000 to 4,000 messages per second per node. So it's really scalable, handles tons of data, and can really do anything that we need it to. So these are a few of the ways that we can set up our nodes in Elixir, cluster them together, and then communicate with them, as well as the patterns that we can use to actually start talking to these nodes once they're together, and what we can use if we need various levels of scalability in a clustered environment. So with that, we've come to the end of my talk, and I really hope that I just gave you guys the opportunity to see how it works in a clustered environment, how we can cluster our nodes together, and what that looks like, as well as how powerful some of the tools that we get with Elixir is that just come with the box. It's honestly so cool. I love Erlang for that because it's been around for so long. We have so many tools that are just built right into the box with us. So I encourage you all to take a look deeper into the Erlang docs, and just to remember as well that we can always build great things with the box.